Also IR and NMR. I tried my best to replicate them. The NMR is a little easier to draw. This one, you'll see it has some peaks around the 3,000 and then not much. The next peak coming up is at about like the 1600 mark. And then it has a number of peaks below that. Okay? And so, let me tell you what I get out of this. First of all, here, because this splits the 3,000, I know there's alkane tendencies because that has below 3,000. I know there's alkene or alkyne tendencies because that's above 3,000. So I'm expecting there to at least be a double bond here and just normal alkane stuff. This peak is about 1600. It's too low and not large enough to be a carbonyl. So I know this oxygen is not a carbonyl. So I'm thinking more ether. Okay? That's really my next best possibility. And then there's other peaks here that I don't worry about. Okay, and then we have integration 1, 1, 2, 2, 2. This one's kind of messy, so we'll do our best here. Let's take a look at this though. This is C5. If this was fully saturated, it'd actually be 5 times the H's would have to be 2n plus 2, or 2 times 5 is 10 plus 2 is 12. So actually, we're 4 off, or the difference in the hydrogens is 12 minus 8, or 4. Divide that by 2, there's 2 degrees of unsaturation. So that could be 2 double bonds, a ring and a double bond, that sort of thing. So I think any of those could be possible. If it's a straight chain, or if it's a ring, I think there's oxygen in it. Okay. So I'm sort of leaning towards the ring and a single double bond, but I guess anything could be possible. All right. So I think the NMR is going to give us the rest of the information that we'll need. So let's look what we have. We have this one hydrogen that's way up there. And one thing I might not have said in some of the other videos, sometimes if you have a hydrogen that is on an alkene, okay, so it's in part of the alkene, sometimes you only see a singlet, okay, so you won't see that fine structure of the splitting. So even though if there's neighboring hydrogens. So this could be, say, on an alkene next to other hydrogens, but we're just seeing a singlet, okay? But anyways, we know there's one hydrogen here. This hydrogen up there, that's next to a couple other things. Since those are the highest peaks, they're above 4, I'm kind of guessing that they could be right on the alkene. So sometimes hydrogens right on the alkene can be pretty high. And then one of these two, I would say, are hydrogens that are right next to the oxygen. Okay? So the oxygen's somewhere in that mess, but usually hydrogen's right next to oxygen's a little close to 4, but usually more 3 to 4. So I'm kind of leaning that these two, which is probably 2 hydrogens, notice this adds up to 8, the integration. So I'm kind of thinking, because usually right next to an oxygen would be 3 to 4, I'm kind of thinking that this right here would be a CH2, and it's next to an oxygen. Okay? That's what I'm thinking that peak right there is. Since these 2 peaks are higher, I'm kind of thinking, and they both have 1 H, I'm thinking it's something like this. So one of these, this one right there, is next to something that probably doesn't have hydrogens on it, so there's no splitting, but this one is next to, say, a carbon with some amount of hydrogens, 2 or 3. So that's this one. Oh, yeah, from there. Because it's giving this multiplet sort of look there. So looks from the diagram that I have that could be a quartet, but it is a little hard to read. Even NMR that I have, the original, is pretty messy. So it's definitely a multiplet. So I'm kind of thinking these are close to each other. This could be, of course, bonded to something else. So right now, I think we have something like this and something like that. Now let's go over to the other side there. Those are as messy. How I drew them is as messy as it looks on the original. They're both pretty ugly looking. We can at least say they're multiplets, but I think they're the furthest away from the double bond or the oxygen. And it looks like they're both CH2s. They're both in the normal kind of alkane range. So I'm kind of thinking it's a CH2 and another CH2. Okay? So that's why I drew those over here. I didn't know how many. I know this is a multiplet, so I thought there's probably CH2s here. And I guess CH2 versus CH3 because all the integrations are 1 and 2. So, I think this side, since it's giving a singlet, is probably next to the oxygen. Okay, there's no hydrogens here to cause a split. Again, often, not always, hydrogens, you can't see the splitting of hydrogens that are next to each other on the alkene. Sometimes you can. So, I kind of think, I'm going to put this picture next to this picture. So I think it is, if I flip this picture, I think it's a CH2, then a CH, then a double bond, then a CH, and then an O. So I flipped this picture right here, and I think that connects to this picture, which is a CH2. Now, notice I don't have any integrations that are 3s anywhere. Because there's no 3s, I'm thinking that this is not, not what's it's called, not a straight chain. Because if there's a straight chain, I have to have a methyl somewhere at the end. And it looks like I don't have a methyl anywhere at the end here. So I'm actually thinking this is a ring. So far I've drawn 1, 2, 3, 4 carbons. So I think there's another CH2, one of these. There's 1, 2, there are several CH2s it looks like here. 1, 2, 3 CH2s flying around here. And I think this is bonded to itself like that to make some sort of ring that has 6 members. So let me kind of draw this out over here as a ring. So it'll be a 6-member ring. One of these is an oxygen. Right next to the oxygen is a double bond. And then there's going to be 3 CH2s, 1, 2, 3. One of the CH2s, this one, is closest to the oxygen, which would be that one. So if I number these, like of A, this is B, this is C, this is D, and this is E, let me label those carbons over here so you know which ones I think are which. I think A is this one, because it's the most highly shifted. It's next to oxygen and a double bond, so it's shifting it way up there. It's a singlet because there's no hydrogens over here to shift with. I think this is B, because again, it's just a single H. Also, is given a multiplet because it's splitting with this one down here. Okay? And it's highly shifted because of the double bond. And it's sort of close to oxygen. Okay. Let's see. The next one, that C1 over there, I'm kind of thinking is this right here. And the reason is it's right next to the oxygen, and a 3 to 4 for a carbon, for hydrogens next to oxygens is pretty reasonable. And then D and E, I don't know if I'll be able to distinguish, but I think they're both right there. A little hard to tell which one is which, but one of these is D and one of them is E. Okay? Now let's go back to the NMR spectrum. The double bond is on the left-hand side of this 3000, higher than 3000. This alkane parts are on the right-hand side, this lower part. And then I knew it was most likely an ether because there was no monstrous peak right here at the 1700 mark. This is more like at 1600, and it's not big enough. The carbonyl peak is huge and goes all the way to the bottom of the diagram of the spectra itself. So I believe this is our answer right there.